All right, welcome everyone to the Chemistry 3-4 Head Start lecture for January, presented by ATAR Notes. My name is Josh, and I'll be your lecturer for today. So just to start off, I'd like to thank ATAR Notes first of all for providing the opportunity for me to run these lectures and for all of you to be able to access these free resources and lectures that essentially many companies would have as a paid resource and something you'd have to pay to get involved with. ATAR Notes has been running these free since about 2007, and since then they've expanded greatly into New South Wales, Queensland, WA. They've even expanded into different streams of and ways of getting you information, especially through some of their various free resources, such as their study notes. You can find online that they have a big sort of bank of study notes. They also have these lectures, they also have discussions and forums, and they have some videos available, particularly like this one, which will be available afterwards. And they have things like their newsletters and articles, etc. We also as well have some paid resources. So on top of all the free resources that we do, we have what we call ATAR Notes Plus, which is a subscription-based platform where you get access to all of the study guide texts and all of the topic tests that we have produced, as well as a fair proportion of company exams, particularly NEEP. It's a company that was run by ATAR Notes in the last couple of years. What you'll find is that this resource also comes with an AI answer bot, which has been trained. Essentially, you have to train AI these days, and it's been trained in VCE, which is a really interesting thing. It's really, really useful and can answer really complex questions. There's obviously a limit to its complexity, but it is very, very, very good for what technology that is very, very new and is only getting better. You can still buy the topic tests and the study guides brand new. You can buy them as a hard copy that's still available. That's not going to go away anytime soon. But we also have this, and then we also have a tutoring program called TuteSmart. You'll find throughout this lecture series, if you scroll through all the lectures that we're running, there will be some lectures onto ATAR Notes Plus and a program called TuteSmart, which is a tutoring company that I work for. I run a chemistry class, and I have 1 or 2 students, but that's about the limit of my availability. But essentially, what you find is that through that program, you get a much more interactive way of chatting with us ATAR Notes lecturers and us ATAR Note tutors. So, start off with just obviously a bit of a welcome. It's the first year of the new study design, and it's following on from the Unit 1-2 changes that you would have done last year. So, for all of you who did Unit 1-2 last year, which I'm assuming is all of you, you will have noticed that there were some significant changes made to the study design, and your teacher would have emphasized this is a new study design. So all the stuff that you're going through is different, etc., etc. So that is a really important point, that this year we are following on from that. So what you'll find is everything from there has changed. And then just a quick thing about who am I. So obviously my name is Josh. I am in my final year of medical school. So technically it's my 6th year at uni. I've done a research year as well. So I'm at Monash University, undergrad. I've been tutoring all 5 of the years so far that I've completed. I'm coming into my 6th year of tutoring. I mainly specialize in chemistry. I can do biology and further. I used to very much specialize in further, but have moved away from doing that as much. I still run the lectures for it, but I don't tend to do any sort of tutoring for it as much anymore. Outside of that, I'm from Bendigo, so I'm not from Melbourne, but being in Melbourne, it's a lot of fun, one of those things. There was meant to be photos come up on that, but I think I might have accidentally deleted them. Nonetheless, the rest of this is sort of what are we going to be doing in this sort of session. So what's really important is that, first of all, we're going to have 2 blocks. Now, there won't be any break between the blocks. This is a recording. You are welcome to take a break at any point in time. I do suggest in between the 2 blocks taking a break. So for the first 40 minutes, I'm going to go through some tips. I'm going to go through green chemistry. Now, you all will have at least have an idea what I mean by green chemistry, given that you did the new Unit 1-2. For those who, did Chemistry 3-4 last year, they'll have no idea what I mean by green chemistry. This is a brand new concept that they've really made a big part of the chemistry sort of guideline. When I say they made it a big part, it was only very, very briefly a part of Unit 1, 2, and like 1 dot point in Unit 3-4. It's now a significant proportion of dot points in Chemistry 3-4, and you will have done a fair bit of it in Chemistry 1-2. So I really want to focus on it, and also particularly because they've made a real point in the study design of emphasizing that green chemistry can apply to all of the Chemistry 3-4 topics. So all of the Chemistry 3-4 topics, no matter if it doesn't say anything about in its dot points about green chemistry or anything like that, it is a potential for it to come up. And that's really important that you understand that that can come up and that can work like that. And then for the last sort of 80 minutes, we're going to start Area Study 1. Now, what's really important is Area Study 1 now is huge. For some reason, they decided to get more stuff and put it into Area Study 1, Unit 3, than what it was already the biggest topic. So we already had probably the biggest topic, probably the most content-heavy topic. It probably wasn't the biggest topic, it was probably the most content-heavy topic. And they've added more stuff to it. So don't be alarmed. You might say, oh no, is there more things I need to know? They've actually gutted Unit 4. Unit 4 is just proportionally a lot smaller now. Organic chemistry has sort of been synthesized a little bit more and summarized down. They've also completely cut out analytical chem and made it its own area of study. And then food chem has just sort of been chopped up, and they've taken about, I'd say, maximum 30% of it and sprinkled it throughout the rest of the area of study. So they've removed a whole area of study. They've split up the big area of study from Unit 4 into 2 area of studies, maybe made the analytical chem a little bit more detailed because that in itself wasn't big enough to be its own area of study, and now it is. But beyond that, they've just cut out a whole area of study and sprinkled a little bit of it through. That's about it. They have gutted a little bit of the fuels. You'll find that fuels is now less in depth. But essentially fuels, there's a little bit of food chem in there, and then there's a natural cycle content, which we'll discuss at the end. And then there's also redox basics. So redox basics still falls under Area Study 1. We won't be going through that today. We won't be going that purely on the basis that we just don't have the time. In a 2-hour lecture, we are limited. And given I want to sort of set up your year with green chemistry and tips, we won't get through to redox. But don't stress, the lecture that comes in the middle of the year, not the middle of the year, sorry, the middle of term 1 and term 2. So that'll be around March, April, probably start of April. That lecture will cover redox, and then it will move into equilibria and electrolysis. So that lecture will cover the rest of Unit 3. This part of Unit 3 will be covered today, and then so forth. So then as we move into the middle of the year, that lecture will cover the start of organic chem. We'll also start to do some sort of exam preparation at that point. So we'll discuss how should you approach an exam, how should you approach exam study, etc. And then after that, we get into the term 3 holidays. You should be ready for your exam. We'll cover the rest of the content, analytical chem, and do a little bit of a summary in how you should really approach the exam those last couple of weeks. So the 4 Chemistry 3-4 lectures that will be produced throughout this year will follow on from one another. They're not going to be repeats, not going to be rehashes. They will follow on. They have a pathway, and they're sort of set up in a sense that you shouldn't be here to learn the content. You should be here to get a brief understanding of the content, and maybe that is learning, but I don't want you to know the ins and outs and every single little detail. There is content today that is left out from even these points if I wanted to go into super detail, but I'm not going into super detail. I want today to be a very shallow understanding of what the content is. So then when you learn in class, you've seen the big ideas, and then the little ideas will make a lot more sense. So as we push forward, as I said, it's important to understand that today's lecture doesn't even cover all of Unit 3 of Study 1. I'm thinking, why am I even here? It's really about building good habits. The start of the year is about building good habits. If you have good habits at the start, you'll be fine at the end. It's really important that I want you to build an understanding of green chemistry, as I've already emphasized. This will feature throughout every area of study. And it's also really, really important to understand the sort of question techniques. There's a couple of techniques we'll go through and some skills such as significant figures. And then we'll give you a small head start on the content for the year, really. So this is how the units are built. So we talk about how chemistry sort of powers our lives, and we go through sort of fuels, then we go through electrochemistry, then rates and equilibria. Now, what's really interesting about this is electrochemistry is sort of broken up into two. You find the basics are with the fuels, and then the advanced electrolysis is with rates and equilibria. So it's sort of a bit frustrating to learn, because you do your fuels, and then you go and do a little bit of redox, and then you sort of forget it. You go, all right, now I'm going into rates and equilibria one, and I keep continuing on with redox. It's a bit of a weird way they do it, but they just do. So it kind of cuts. You then do rates and equilibria, and then you come back and do a bit more electrolysis. And that's how those two area studies sort of fit in together. Then we have Unit 4. So Unit 4 is how chemistry explains life. And we have experimental design, organic chem, and analytical chem. So this used to be experimental design, organic chem with analytical chem, and then food chemistry. Now what they've done is they've split those two up. And that is essentially how the units run. Now, experimental design is really interesting. As much as it's part of Unit 4, it can come up wherever. It's another one of those topics that is very broad ranging, much like green chemistry. It can come up absolutely anywhere. And essentially what happens with it is you will do a poster, or you do like a practical report, but usually it's done as a poster, and you'll be expected to do an experiment on one of these topics and then apply experimental design concepts to it. And then I just quickly wanted to point out, because I know there'll be a vast proportion of you that will receive notes from an older sibling or a friend in the year level above, or you might go and have some tutoring and you get given some notes that are not relevant to the new area of study. They're the old study design. Now, what's really important is those notes will still be useful. As much as I want you to do your own notes, they are still useful, and don't throw them out. What you need to know are what are the changes. So Unit 3 Area Study 1 changes. So what is being removed? What is being removed is the emphasis on crude oil. You'll find that in the older exams and the older study guides and so forth, there's a massive emphasis on crude oil. Even if you don't know what that is, don't worry. But crude oil is sort of the raw component of just like petrodiesel. Crude oil, you still need to know about it. You still need to know little bits of detail about it. We're actually not even going to talk about it today. It's more of a smaller subtopic, but it used to be a really big topic. You used to have to know heaps about it. You don't anymore. And then they've removed the emphasis on the comparison of cells. So what you'll find is if you read the old, and I don't want you to, but I've done it for you. When you read the old areas, the old study design, you find that there was about 4 dot points in a row that were like the comparison of this cell with this cell, the comparison of this cell with this cell, the comparison of that with that, the comparison of that with that. Those have all just been removed. Now, it doesn't mean comparison questions are being removed. There will be comparison questions. They love them. They love a comparison question. But the idea is that the emphasis on the comparison of cells has been removed. And then what has been added or altered? So fuel sources, or PF, of the body have been pulled from Unit 4 Area Study 2. So this is a little bit of that food chem that's been sifted through. As you can see, it's one of our subtopics today. We will discuss it. It will only be about 10 minutes, but we will discuss it. And then, cellular respiration and photosynthesis has been added. This is brand new. This is our natural cycle. It sort of builds on from that sort of fuel sources of the body. So looking at the cellular respiration and photosynthesis sort of cycle. And then we have the green chemistry application that comes with it. So then my next point is, you're at the start of the year, you've just done Unit 1, 2, you've probably done an exam, now you've been on holidays, and you've probably been like, I don't really care about, chemistry anymore. That is fair enough. If you don't care about chemistry anymore, completely reasonable. Once you move into chemistry 3, 4, you'll be like, all right, now I care about it again. When you do, this is what you need to know. This is what is helpful to know from Unit 1, 2. So need to know is super important. It's like a must. You must remember this stuff. So you must remember the concept of the mole. And then sort of the writing and balancing of chemical equations around that, and then the stoichiometry calculations. So the mole is really important. As much as you might say, well, I know what a mole is. It's 6.02 by 10 to the 23 molecules. Sure, that's not really all that useful. I'm more talking about working with moles. So having the ability to manipulate moles within an equation, and then writing that out, having the ability to work with it with stoichiometry, so using your moles equals mass over molar mass, using your concentration calculation, so moles equals C by V, looking at those sort of calculations that you need to work with. Also sort of in the gaseous form, we will talk about it again today, but the universal gas equation does come up again in year 12. It's a big content, it's a good aspect of it, big aspect of it. And then working with concentrations, and this is particularly important for things like titrations. I'm sure you did titrations last year, and I'm sure you heard all the memes. Titrations are all of chemistry. Yes, they are. You do need to know your titrations. They do come up, and they are a vast and pretty strong aspect. HPLC does come up, and the annoying thing about HPLC is a lot of schools ignore teaching it. They sort of expect you to remember it because it's smallish, but it will be worth 1 or 2 marks in the exam. So do remember your HPLC. And then for all of you, which is new, in Unit 1, 2, you learned some green chemistry. Those concepts still apply. Please remember those green chemistry concepts. Then we have our inter versus intramolecular bonds. The super detail about them is not that useful. You really just want to know the strengths. When are they present, and the strengths. Redox basics. Although you do completely cover this again, it's important to sort of have that understanding of it because you'll probably go through it a lot quicker. Same with organic basics, so organic chemistry. Again, you're going to cover it all again, but it's also like if you know it already, it'll be a lot easier. And then acid-base reactions, although they don't commonly come up, the idea behind them is useful, particularly in things like titrations. And then how is chemistry assessed? This is something that you should all know at the start of the year. So you start off with Unit 3 worth 16%, Unit 4 worth 24% because they are bigger. The exams are 60%. The exam is worth the majority of the year. It's big, it's difficult. You need to make sure that you are ready for it. So it is a long way away, and I don't want you to stress about it, but just to go through some points about it, it's 120 marks. It's 120 marks in 150 minutes. 150 marks, it should say 150 minutes. Oops, my bad. So it's 120 marks in 150 minutes, but it has a 15-minute reading time as well. So I would argue that it's not just 150 minutes, it's 165 minutes. Right, now let me get rid of my pen. Why are you not letting me get rid of my pen? All right, we're working with the pen now. There are 30 multiple choice. There are 90 short answer marks. This is usually over 8 to 12 questions. So there's 30 multiple choice questions. There's not 90 short answer questions. There is 90 marks. This is usually over 8 to 12 questions. Now, when I say 8 to 12 questions, that's like a question that has subparts. So it'll be like question 1, and then it'll have like 4 parts to it. So there'll be 4 questions within it. And then also really important, the exam is difficult, but it's also really fair. And I think that's something I want you to get your head around. Lots of students go into the chemistry exam thinking, oh, this is just going to be really hard. And they've made it hard because they're not being nice. That's not true. The exam is actually reasonably fair. The exam is difficult, but it is fair. There's a large variation of questions. There are some very straightforward, basic recall questions. But then there are some far more complex interpretation-based questions. They need to split you up. They need to get the 50 student from the 25 student. They need to split you up. That's how they do it. They have easier questions. They have more difficult. It's a very fair exam. I think chemistry does it really well. And although the questions are mostly segregated into their sort of topics, they do overlap at times. There is a distinct overlap in some questions. So it's important to practice integrating your topics together, not just doing one at a time. So further to this, let's have a look at sort of just my 3 big tips. So my first one is to work with a study design. So the study design is intended as a guide. And it's really important that you utilize it as one. So the study design, study guide, whichever one you want to call it, has many examples, definitions, suggestions on how to sort of approach the content for the exam. Utilize this. So utilize it as a checklist. Go throughout the year and familiarize yourself with the topics, and especially the ones that they emphasize. They do emphasize some topics more than others, so be prepared to be on top of that stuff. Meet your new best friend. So if the study design does not become your best friend, the data booklet will. This data booklet will look probably pretty foreign right now. You're probably going to open it up, so you can just search up VCE Chemistry Study Guide, or come as a PDF. Sorry, not study guide, sorry, data booklet. And you'll have a look at it and you'll be like, this is really foreign, what is this? It's super handy, and as you progress through all the content, you'll start to understand what everything is. I would suggest having one printed out at the start of the year, or your teacher should have copies of them somewhere, and then sort of label and annotate it as you go. Now, really key point, in the exam, you get a fresh one. You do not get your data booklet that's all annotated. You get one that has nothing in it. I do apologize, I have a bit of a cold at the moment. You get one with nothing in it, and so the annotations will not be useful then. So really, really important that you have as you go further into the year and you start to do some practice exams, you use fresh ones, you don't use your annotated one. Now, your annotated one will be useful throughout the year as you learn, but when you get to the end, you want to start using fresh ones. And then my next point is sort of a bit of a self-explanatory one. I want you to work hard, but more importantly, I want you to work efficiently. Now, what does that mean? That means I want you to prioritize study that will have the largest possible impact on your result. And this essentially just means to focus on areas you struggle with, and even if you dislike it. Now, for me, it's really funny. I'm going to use an example outside of chemistry. For me, I remember back in the day, I detested English. I hated English with all of my body. English was my least favorite subject. It still is. My spelling, my grammar is still shocking. But I disliked English, but I knew English had to be one of my top 4. So what did I do? I put my head down and my bum up, and I grinded out. A large proportion of my study in Year 12 was to English, and particularly to, I don't remember what they call it, to be honest. That's how long ago it was, and I haven't touched an English essay since then because I detest English. The whole getting an article from a newspaper and breaking it down and writing about it, that whole aspect was my least favorite. I detested that, and yet I knew I had to do it. So I did it. I practiced, and I got really good at it. Same thing with chemistry. If there is a topic you dislike, for me, it was electrolysis. I did not like electrolysis. So what did I do? I focused on it. It was actually the one that I did really average in for all my SACs. And that's where I sort of realized I disliked it. I was okay while learning it. It was a bit, yeah. And then I did the SAC night, just really did not like it. And then I was doing study afterwards. I really did not like it. But I realized to myself that I was struggling with it. I needed to find a way to get better at it. So I practiced, and I managed to do reasonably well in my electrolysis question on my exam. And that's what's really important. So throughout the year, you need to learn how to answer questions. It's a skill itself, but you also need to focus on the areas that you are struggling with. It's a really key point here. Always review your SACs and focus on the errors you made under pressure, because you make different errors under pressure to what you make when you are, not under pressure. Now, very quickly, I just wanted to point out significant figures. It's something that is distinctly put in the study design, but some people sort of neglect to learn it. Now, really important. Significant figures is a very complex topic. It's maths, but we sort of need to know it very briefly for chemistry. Now, why? Do all questions have significant figures? For the exam, you are going to do significant figures on every single question, but does not mean every question will be marked with significant figures. Notoriously, chemistry has allocated 1 mark to 1 question for significant figures. And you know what they've done? They haven't told anyone what that is. And they haven't told you what that is while you're sitting in the exam. So, for you, you're like, well, how am I meant to know which question to do significant figures on? You're not meant to know. You're meant to do them on all of them. And if you do them on all of them, you'll get the one that has significant figures marks. So, How do they work? There's three major rules. All non-zero digits are significant. Any zeros between two significant digits are significant. So this zero here is, but these zeros at the end are not because there's no significant digit after. Same thing here, this one is significant, this one is, but this one is not. A zero which is after a significant figure and after a decimal point is significant. So if you could write that as 3. So this first one here, I could just write that as 3. But because I wrote that as 3.00, that means I have 3 significant figures. Same thing here. I could have written this as 4.4, but I put a 0 on the end, so it counts. Now this one's interesting. This first 0 does not count, because if I had to write this out more simply, I'd write 0.012. It would be 2 significant figures. These 2 do not count. Because I've added these 2 zeros, this becomes 4 significant figures. Now, what does that mean for a question? Well, that means when I answer a question, I need to look at the significant figures that are in the stem of the question. So the question on the paper, look at the stem, look at the numbers that are in the stem. If there is a number that is written like this, I need to answer my question. I do my maths and I answer it as a significant figure of 3. So 3 significant figures. If my answer is 2.4, I need to write 2.40 because the question had 3.00 in it. Now, example, 30.0, how many significant figures is this? Let's go through it. So, here you go. The 3 is a non-zero, so it's significant. The first 0 at first seems not significant. But then the second 0 after is after a dot point, so therefore it's going to be significant. And then the first 0 then becomes significant because it's between the 2, so therefore I have 3 sig figs, or significant figures. Also, just some other aspects. If you are given 2 numbers to divide or multiply, maybe you're doing like a moles calculation, and one of them is to 3 significant figures and one of them is to 4, you go to the least number of significant figures. Same with addition and subtraction. If you are adding numbers and you've got less significant figures, you go to the least. All right, green chemistry. So first of all, with green chemistry, what I'm going to do is I'm going to go over a little bit of Unit 1-2 revision. There's actually going to be 2 slides on it, and maybe the third slide is a little bit of revision, but nonetheless. First one is the continuous cycle. I have pulled that exact quote from the study design. That is literally what is in the study design. That diagram is in the study design. That is what you need to remember for this year. That is what you will have covered last year. You will have covered this whole idea of linear versus circular economy. The whole idea that, let's use copper wiring as an example. Copper wiring is pretty expensive to make these days because copper is becoming less common, harder to sort of work with. What you find is that you have mined some copper, you make some copper wiring, you have distributed it out, you've used it, but then you don't need the product anymore, so you go throw the product out. But what if you remove that copper wiring? You remove that copper wiring, you send it to a recycling company, which will then take that copper wiring, it'll either melt it down and remake copper wiring, or if it's in good enough condition, it'll just it'll just sort of straighten it back out, give it a little bit of a polish up, do whatever it needs to just to make it back to brand new or as close to brand new as it can, and then it remakes another product. And it utilizes that copper wiring. And the whole idea is that copper wiring stays in the system, or that copper stays in the system. Now, if you just throw it out, well, then that's a waste of copper. And that's linear economy, throwing that stuff out. Now, greenhouse gases. Greenhouse gases are gases in the Earth's atmosphere that absorb and trap heat, assisting to regulate and ensure that the planet has sufficient temperature. Now, what's really important about greenhouse gases is you need to understand the process by how they work. So, during the day, the sun's UV rays heat up the Earth. So, the sun, it's out like right now. It wasn't out this morning, which is why I have a jumper on, and now I'm getting a bit warm. The sun's out, sends its UVs down, and the UVs sort of enter the atmosphere, and they actually heat up the ground. They don't heat up the air, they heat up the ground. As they heat up the ground, the heat is released, and especially at night. So during the day there is heat release, but it's sort of like proportionate to what's going on around it. at night, there's nothing sort of going on around it, so it's releasing lots of heat. And that's why the ground becomes really cold, and then obviously the outside starts to become colder and colder as that heat is lost. This is released back in the atmospheres and back into the atmosphere, and without greenhouse gases, or GHGs, the heat would essentially just rise and be released from our atmosphere, and essentially every night we'd freeze. We would freeze, and we would probably freeze to death. That's how cold it would get. Greenhouse gases ensure that this does not happen, and they do allow some out. That's the idea. If we have greenhouse gases in their correct proportions, we will trap the correct amount of heat, and we work perfectly well. However, obviously that doesn't always happen, and our greenhouse gases are not in perfect balance. Now, also what's really important is you need to know what the 5 main greenhouse gases are from year 11, and I'm hoping you remember it. If you don't remember it or you want to have a go at it, just pause the video now and just have a quick think, write them down on a page. There are 5 main ones, and then I want you to highlight which of those 5 does not occur naturally. Which of those 5 have we added to the atmosphere now, and they've become a greenhouse gas since we started creating them. So take a minute. I want you to pause, 3, 2, 1. All right, hopefully you are back and you had a go at this question. So there are 5 main greenhouse gases, and these are carbon dioxide, methane, water vapor, nitrous oxide. Those are the 4 natural ones. They're the ones that naturally occur and are just there. Then we have fluorinated gases. So fluorinated gases are gases that have a fluorine molecule on them. They are very harmful to the environment, and they have contributed to this rise in greenhouse gases and this temperature rise of our planet because we've synthetically produced them, and they were never a greenhouse gas, and now they are. So then we sort of discussed from here the enhanced greenhouse effect. You will have covered this last year, but you cover it in a lot more detail this year, more on the basis of that you start to do some gas calculations and determine, how much of this has been produced, how much of that has been produced. Sort of that aspect of things. The enhanced greenhouse effect is what we currently refer to as the major cause of climate change. It's due to an increased proportion of greenhouse gases, particularly fluorinated gases, from fuel and infrastructure production. Very simple and basic definition of it. The increased ability for the planet to absorb and retain infrared radiation has subsequently begun to slowly warm the planet. This has shifted climate norms and increased sea levels, which is due to sort of the glacier melting from the increased pole temperatures. So the poles of the planet are getting warmer quicker than the middle of the planet is getting warmer. It's just, that's a little bit of physics. You don't need to worry about that side of things, but it's something that you need to know for chemistry, and then you need to explain it in a chemical point of view. You need to talk about what are the greenhouse gases, and then this is where that green chemistry comes into it. What if we can minimize greenhouse gases in our production? Will we do it? Should we do it? Etc. Something like that. Now, what's really new for our 3-4 is that the VCE study design has placed this significance on these green chemistry principles. Now, you may have talked about these last year. They're not sort of put in an area of study. They're put at the start of the Unit 3-4 study design, and it's sort of just said you need to know these. So a lot of students that I've already talked with have already done this in Unit 1-2. They covered this in Unit 1-2 because that's what their school wanted them to get their sort of head around. If you haven't, that is okay. It is essentially aimed for you to start this in 3-4. So you're just doing what VCE wants. Now there are, I believe it's 7 concepts you need to know. The 7 concepts are atom economy, catalysts or catalyzing, design for degradation, design for energy efficiency, design for safer chemicals, prevention, use of renewable feedstock. So these are 7 essentially definitions and concepts that you need to know to answer green chemistry based questions. So you will get a question, and it will be, something about using a fuel cell instead of using standard combustion. You may have no idea what I'm talking about there. Do not stress, but it is something you will learn. And you might sit there and go, what is that all about? What's really important is that is one of these. That is using some of these topics here. So when we use a fuel cell, we're using things like designing safer chemicals, and design for energy efficiency. And you'll understand why, as you learn this stuff. But it's what I would refer to if I was asked why I was making that decision in terms of green chemistry principles. I would say I'm making that decision because of this principle and this principle, which state that da 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 da, and then sort of refer it back to the example I was discussing. So then we have each of their definitions. Now, what I've done is I'm going to mix them up. So I think this is a really good activity. It's something that I run with my chemistry classes, and I thought, you know what, I'll give you a little, taste of what we sort of run in our sessions at Shoot Smart. So you're getting a little, little sprinkling of what we do before we even do it. But nonetheless, I want you all to have a go at this. I want you to match up each of these concepts. So what you'll find is that there are 7 concepts, there are 7 definitions. I want you to match them up. So, you go 1A, 2B, etc. It's obviously not going to be in that order, but don't worry. I want you to have a go at that. This shouldn't take you more than a couple of minutes. And you may not know. You may read through and go, I have no idea what some of these mean. I have no idea what some of these definitions are talking about. That's okay. This may be the first time you're doing it, and that's fine. But I want you to have a go at it. So what I'm going to do is I'm going to tell you all to pause, and then I'd say take 5 minutes at least. If you finished earlier, that's okay. And then unpause, and we'll go through it. So 3, 2, 1, pause. All right. Hopefully you are back. By the way, I do love my coffee. That's why I've got a coffee here. Let's go through each of these. So we'll start off at the top of the concepts, and then we'll give it its definition. Now that's meant to say definition up there. I do apologize. Concept, it's meant to say definition. I do apologize for that. Nonetheless, let's have a look. So we got atom economy. You should remember atom economy from last year. Atom economy was where the atoms that we used at the start of the chemical equation were as close to 100% used in the desired product. So if only one of the 2 things that were produced was the desired product, we want to maximize that percentage. So which of these talks about that? So we need to look at things like reactants or the start of a chemical equation. No. Also no. Look, that one sort of gives it away for which one that one is, but it's not. It's better to prevent waste. No. It has to be G, but process should be designed to maximize the incorporation of all reactor materials used in the process into the final product. So that is exactly what atom economy is. So therefore, I'm going to say that is G. Apologies, I'm using my old Mac mouse pad, and it's not very good for doing things like that. All right, atom economy is G. 2, catalysts. So remember that catalysts, what they do is they provide an alternative reaction pathway, and they use essentially less energy to get what they want. So essentially what you do is you're adding in a catalyst and they get what you want utilizing less energy because they provide an alternative reaction pathway. So once again, reading through, I remember there was one that talked about less energy. It was B. These should be selected to generate the same desired product with less waste and less energy and reagents in the reaction process. That is a catalyst. That is a perfect definition of a catalyst. Answer here for 2 is B. All right, 3. Design for degradation. So we'll read from the top. We're not going to do B or G. A, chemical products should be designed so that at the end of their use, they break down into harmless degradation products and do not persist in the environment. Well, that sounds pretty good. I'm just going to check the others. Chemicals should be designed to achieve their intent of minimizing toxicity. I'd say it's safe for chemicals. Raw materials feedstock. That's in feedstock 1. So I have maximum energy. No. Yeah. So 3 is A. All right. 4, design for energy efficiency. Well, we just read that one, and that one was down here. So process should be designed for maximum energy efficiency with the minimal in a negative environment and economical impacts. I'm pretty happy with that. I think 4 is E. And then we go to 5. 5 was safer chemicals. Again, we read this one just before. That one was here at C, which is designed to achieve their intended function with minimizing toxicity. Makes sense. All right. And then we have prevention and we have use of renewable feedstock. We have D and we have F. So we've got raw materials feedstock should be made from renewable materials rather than from fossil fuels. It is better to prevent waste than to treat or clean up waste after it's been produced. Well, it's pretty obvious which is which. Prevention is going to be the prevent waste one. They use the word in the definition. Not really a great way to do it, but that's what they did. And then the raw material feedstock is mainly, plant-based. That is going to be use of renewable feedstock. So that is our aspect here. So we go 1G, 2B, 3A, 4E, 5C, 6F, 7D. That is how we go about it. They are our definitions. These have been pulled straight out of the chemistry study design. These are the definitions they provide you. So you should know these. As much as I don't want you to know word for word, I want you to know them pretty reasonably. I want you to be able to explain each of these 7 concepts. And this is something you should practice throughout, particularly throughout term 1, so that you can apply these in your chemistry-based or your green chemistry-based questions as they come up. So then just our last point on green chemistry, and we're actually not going to cover any of these green chemistry points today. There are 3 explicit examples of green chemistry that they want you to know at the end of your exam. So there will be more that they'll apply green chemistry to, but these are 3 that they have explicitly said you need to know. Now, the only one that's part of Area Study 1, Unit 3 is fuel cell sustainability, as per this green circle. However, we're not going to cover it today because we're not going to get up to redox, so it will be covered in the next lecture. But it's really important that you understand that there are some examples VCAR has made distinctly they've distinctly said that you need to know this. Like, we're going to ask about it. I'm telling you now, we're going to ask about it. That's what they've said. So, fuel cell sustainability, what does that use? So these are the concepts that you should refer to when discussing these. Same with equilibria in industry and green hydrogen. Now, each of these points will come up at another point in time. Do not stress. But just wanted to point out these are the ones that I've already gone through these in going through the new study design and producing content for them. I've already gone through each of these concepts. I've gone and done the research and discussed what's sort of going on. I've also gone through and picked out the ones that I feel are most relevant, and I've found that in some of the newer content being produced, especially throughout ATAR notes and by other tutors, we've sort of agreed that these are the ones that are the most relevant for each of these concepts and what you should probably discuss in discussing these concepts. You can find these dot points in the study design, which obviously I've got my data booklet here. But I've got my study design here, so you can find, if you scroll through this here, you will find the dot points. My word is struggling. I think my computer's doing a bit too much at the moment. But as you can see here, I just want to find that dot point. Here is that question in green chemistry. Contemporary responses to challenges and the role of innovation in the design of fuel cells to meet society's energy needs with reference to green chemistries. They've given these 2. So they've said design of energy efficiency and use of renewable feedstock. We've added catalysts to that because we feel like catalysts are something that are utilized in fuel cells. You'll find them in the electrolyte. They're really important to it to make fuel cells work, and thus it's a concept that should be added onto that. So as you can see there, the dot points have explicitly asked you to know this, something you do need to learn throughout the year. So we're about 45 minutes in, and we're about to start Area Study 1. If you haven't taken a break or you're feeling a little bit like, God, that was a lot of stuff to take in, please feel free to take a 5-minute break, just pause, and just, go to the toilet, get yourself a coffee, like what I'm doing right now. And then come back, because we've got about 75 minutes to punch through the first, I'm going to say 2/3 to 3/4 of Area Study 1. It's probably about 3/4 of Area Study 1. Redox probably only makes up about 25% of it. It's pretty small. But that is what we're essentially going to go through. So I've broken this part up into 3 distinct topics. I think Area Study 1 breaks into 3/4 distinct topics. I think food, chemistry, and the natural cycle sort of interlink. Same with, to be honest, fuels and then those 2, they sort of interlink. Those 3 are very similar. However, you can break them up into three distinct sort of features. I think they're three distinct features. And then you have your fourth feature being redox. So I think there's four distinct topics, subtopics within this area of study. Now, these are, they're all going to integrate into each other. That's why they're in the same area of study. But they are sort of four distinct subtopics. So if you are to, make a summary book, or you are to go about writing some of this stuff out, I would say they are your four distinct topics. So let's start off with just the most basic slide. What is a fuel? So it is distinctly quoted that you need to know the definition of a fuel. A fuel is a substance that can be reacted with other substances, leading to the release of energy that can be harnessed for a specific purpose. This is explicitly mentioned in the study design. You do need to know this, and that's just how it is. I can't really give you anything more to it. And then you do need to know renewable versus non-renewable. So a renewable resource can be replenished by natural processes within a relatively short period of time. So, short equals like a human lifetime. So essentially, I like to think of it as we can produce this fuel quicker than we use this fuel. Non-renewable is the opposite. You cannot produce it quicker than we use it. It takes more than, a human lifespan or like a short period of time to produce. Non-renewable fuel is very difficult to get your hands on. Then what we have is, building on from that, we have these ideas of, sorry, my computer's struggling a little bit. Doing the recordings, my computer starts to sound like a helicopter and can lag a little bit. I do apologize for that. We have biofuels versus fossil fuels. Again, I'm using the same colors because biofuels, as you expect, are renewable. Fossil fuels, as you should also expect, are non-renewable. So biofuels are fuels derived from living matter. I've got those two. Well, yeah. I got those two mixed up. Yeah. They are the wrong way around. Whoops, I've copied the wrong. I put the wrong text box in the wrong spot. I do apologize for that. They're the wrong way around. Biofuels are derived from plant matter. Fossil fuels are derived from living matter compressed underground for millions of years. I've mixed those two up. I do apologize for that. But essentially, biofuels, plant matter, produced at the same rate we consume it. Therefore, they are renewable. Fossil fuels are produced over millions of years, and essentially, therefore, are really hard to reproduce. I really hope I haven't, therefore, given the wrong... Have I done the wrong one down here? No, I haven't. Good. I was going to say, why did I mix those two up? Biofuels are biogas, bioethanol, biodiesel. It makes sense if they have bio in front of them. It's going to be bio. Fossil fuels, they're like natural gases, coals, petrols, etc. And so also really important to sort of understand that's how that works. So we're going to go through the three main forms of biofuel now. This is very brief what I'm giving you. There is a much greater proportion of content that you need to go through for these. It's way more in detail. It's not even just much more in detail. It's way more in detail. But I'm going to give you a very brief sort of understanding of each of them. So you have biogas. So this is produced by anaerobic fermentation of plant waste. Now we are going to talk about anaerobic fermentation in a second, so please don't stress. We'll actually not a second. We'll do it in the natural cycle. So it's probably a little bit away, but that's okay. And what's really important is that it's the weird thing about it is it produces the exact same fuel as natural gas, which is what we get as our fossil fuel version of biogas. So it's essentially the fossil fuel gas that we get. We call it natural gas, but it's not bio. So natural gas is a bit of a misnomer. However, what's really important about it is that it produces only about 32% methane, whereas our natural gas produces a much higher proportion. I don't remember the exact percentage, and you don't need to know the exact percentage, but the exact percentage is much larger. Therefore, when you take that gas, we don't really have a way to cleanse that gas in a sense. We don't have a way to get rid of the other gases. Like we have some ways of getting rid of some parts. We can't get rid of it all. So in the end, we're left with, a fuel gas that only is about 32% fuel. So therefore, it has much less energy. Therefore, when you're burning the same volume of that, that fuel, there's only 32% of it that ends up being fuel. Therefore, when you have a full volume of it and the same volume of natural gas, which let's just say, for example, is 70% methane, which is the fuel, this is going to produce a lot more energy than our biogas, which is one of our downfalls of it. But it is produced very renewably. It's produced from sewage treatment plants and landfill in Australia. We put in anaerobic bacteria, and we end up producing gas by methane, which looks like this here, and these sort of little setups are how they work. And then we have bioethanol. Now, bioethanol, that arrow's not meant to be there, but it is. Whoops, why'd that go too far? Now, bioethanol is produced by anaerobic fermentation of glucose via yeast. Again, something we're going to talk about. So we will talk about this whole anaerobic fermentation and all of that. Bioethanol must be distilled prior to use. Now, you will learn about distilling throughout this topic. We won't discuss it today, but you will learn about it throughout this topic. But you'll also learn about it in Unit 4 Area Study 2. So you do need to know it in both. It involves boiling points for the products through large tubes, and then it allows the water to remove in one area and the ethanol to be removed in another. So it sort of purizes our bioethanol. As you can see here, this is what bioethanol looks like, and you'll find that bioethanol is in our E10 fuel. So I'm sure you've been to a petrol station before with your parents, or if you're 18 by yourself, and you've seen that there's this E10 fuel, which is a couple of cents cheaper than normal petrol. The reason it's a couple of cents cheaper is that bioethanol doesn't produce as much energy as petrodiesel. Petrodiesel produces a far greater proportion. But when the fuel is only 10% bioethanol, you still get nearly the same amount. You just get a little bit less. But essentially that bioethanol makes that E10 fuel slightly more renewable in a sense, because you're sort of subsidizing your fuel down a bit by putting some bioethanol in there. Some states like to refer to it as 94. So you know how unleaded we call 91? It means there's 91% fuel or 91% pure fuel. That means there are some, other bits in there. It's not as pure. When we put bioethanol in there, we treat bioethanol as another pure product. So we say it's about a 94. 95 is when you have, 95% of pure fuel, and 98 is your more, it's better for your engine to use a higher grade because it's more clean. There's less byproducts, there's less other things in there. However, some cars are actually not built to be able to take something that pure. They're built around the idea that the fuel is not all that pure. So that's why you can't go and put 98 fuel into a car that's meant to take 91. Although you can, and it wouldn't be the end of the world. Your car wouldn't explode. If you kept doing it, it would be bad for your car. Same if you go the other way around. A car that's built and requires 98, so a lot of these luxury car brands, they require that higher percentage. They don't have the capabilities to get rid of all of the byproducts of 91. You can put 91 in there once and it would probably be fine. It's not great for it, but if you continue to put it in there, again, it'll be detrimental to the car. So that's the idea behind bioethanol. And then we have biodiesel. Now, biodiesel is our closest comparator to petrodiesel. Now, biodiesel is produced by using plant oils or animal fat, so we get triglycerides, and then we do a transesterification reaction. Now, that is a big aspect of Unit 4 Area Study 1. You do not need to know it in detail at the moment. You just need to know the wording. You need to know that you get a triglyceride, you get a methanol. Now, that methanol should be produced renewably. You don't need to know how or where you're getting it from, but you should be producing that renewably, and you need to mention that. You don't want to be using a fossil fuel methanol, otherwise it's no longer a biodiesel. You've just used a fossil fuel. You then do a reaction, and what's left is you get glycerol. Now, glycerol is a bit useless. We don't want it. It's just a byproduct, but it's not detrimental to anything, so we just remove it and deal with it appropriately. And then we have biodiesel. Now, biodiesel is what we want. So biodiesel is polar compared to petrol or petrodiesel, and these both have a very similar energy content. But petrol being non-polar means that it has less intermolecular bonds. Something I said you should remember, you should know the strengths. It doesn't have hydrogen bonds, it doesn't have dipole, it just has dispersion. By having just dispersion, it's less likely to absorb energy and water. So I said hygroscopicity there, and I said absorption of energy. What I meant is sort of the fuel absorbs water, and then that water in turn, when you combust the fuel, will absorb energy. So when your biodiesel here, which I'm talking about, produces, when your biodiesel is combusted, and it has a greater viscosity. It's thicker because of those stronger intermolecular bonds, because it has hydrogen bonds, because it's got oxygens and hydrogens, and because it's got dipole-dipole, because it has a polar aspect, and it's more hygroscopic. What that means is that it actually absorbs more water. That's what hygroscopicity means. It actually means it absorbs water, but I like to think of it as it absorbs energy. What that means is that that water, when it's in with that fuel, when you combust the fuel, the heat is meant to, move the pistons and so forth and get the car moving. If there's more water in there, it actually needs to heat the water first. And so therefore the water absorbs some of the energy as it heats, and therefore you don't get as much energy going straight to the pistons. So that's why it's a bad thing to be more hygroscopic. And biodiesel is more hygroscopic and more viscous, which means it's thicker, which means it doesn't flow as well. So when you get really cold, it doesn't flow at all. It's not useful compared to your petrodiesel or petrol. Now, this is what a transesterification reaction looks like. Please don't stress about it too much, especially at the Unit 3 Area Study 1 level. Your teacher may want you to know it for the SAC. They may say, look, we're going to go through it. We're going to learn it now. So please, therefore, then go and learn it and, spend some time on it. But a lot of teachers will say, oh, look, don't stress about it too much. We're going to go through it in a lot more detail in Unit 4 Area Study 1. So just know the brief, wording of it. You'll learn how to actually do it in this sense, like this diagram here, as you move through. Now let's look at our fossil fuels. So first of all, we'll start with coal. Coal, most common one because we use it so much in Australia. We sit on a coal gold mine, if you like to think of it like that, which isn't really exactly a good thing. Coal is a combustible black or brown rock. It's composed pretty much primarily of carbons. It's the largest source of energy worldwide because it produces electricity. And you really need to know this transformation process. So I like to think of it in terms of like a factory. You can search it up and find like factory sort of diagrams that help you sort of get your head around it. Essentially what you do is you get your coal, and your coal has carbons in it, and it has energy in a chemical form. It's locked within its bonds. You then combust the coal, so you heat up the coal, and the coal produces thermal energy. So as those bonds break, and as the coal sort of breaks down, it releases energy, and that energy is released as heat. And usually what it does is it heats up water. So it heats up a barrel of water, and that barrel of water heats up and boils, so it just continues to boil it, and produces steam. So essentially you've converted the energy from chemical to thermal in the coal, to then thermal in the water, which is steam, and then that steam moves a turbine. So that steam moves up and it moves the turbine, and as that turbine moves, this becomes mechanical energy. So you've moved the energy from chemical to thermal to another version of thermal to now mechanical. As that mechanical turbine moves, it uses a bit of physics, it uses a bit of coil laws, and essentially what it does is it produces electricity. And so therefore you've had 1, 2, 3, you've had 4 energy conversions to get to electricity. Is that good? No, it isn't. 4 energy conversions, even if they all run at 80%, essentially you need to multiply those together. So the rule with energy conversions, which I'm going to grab my calculator out now, is if I want to do it, I would go 0.8, because that's 80%, and I would multiply it by 0.8. That's 0.8 here, plus times by 0.8 here. I'm going to times by another 0.8, put it here, and I'll times by another 0.8 over here. Now that was 80% efficient. 80% efficient is pretty good. That comes out at about 40% efficiency. I hope you can see that there, but it comes out at 0.4096, so about 41% efficiency. That's terrible. And these are not 80%. These are usually a little bit less than that. So you can guarantee that the energy you're getting out of this is nowhere near what you started with. So that is why this whole process of using coal is flawed. It's a flawed process that people are, quite frustrated by in this aspect. There's also this concept here as well about peat, brown coal and black coal. So peat, brown coal, and black coal are just different aspects of carbon that have been, different aspects of coal that have been sort of sitting in the ground for different times. So peat has been there for less and isn't as deep down, so it hasn't been, pushed together and made into this, more pure version of coal, whereas brown and black start to get more pure and therefore have more energy per gram. And then we have natural gas and we have Petrol or petrodiesel, whichever one you want to refer to it as. We like to refer to it as petrol now. It used to be more referred to as petrodiesel, but they're moving towards just petrol. Natural gas is a wide variety of hydrocarbon gases, so methane through to butane. You realize it's a fuel. You find in ground pockets, it's a lot higher percentage of fuel compared to biogas, and therefore that's why you get more energy. Petrol is the refined version of oil that is collected from large deposits under the ocean. So we get oil rigs under the ocean. What do they get? They get crude oil or petroleum, a bit of both, usually crude oil. They then refine the product into petrol, petrodiesel, and diesel. They're just different levels. They're just different lengths of carbon. Petrol is purely usually octane, so it's 8 carbons long, whereas diesel is usually all 16 to 18 carbon long molecules, and then petrodiesel is somewhere in the middle. The reason why petrodiesel is most common is it kind of has a lot of different ones kind of combined. Petrol is usually purely octane, or maybe a little bit of 9 carbon, but usually just 8. And then diesel is usually, in again, a very small range of 16 to 18, whereas everything else in the middle is petrodiesel. Each of these collections, it says here, it's the same length of hydrocarbons. We try to keep them the same. Sometimes there's a couple of different ones, as in diesel, and same with petrodiesel. Petrol, they try and keep pretty pure. They try and keep it mainly octane. And that's why each of these sort of release different amounts of energy. And they're refined through this process called fractional distillation, which you will learn about. It used to be a really big part of the study design. It's now just a smaller aspect, but you do need to know it. And it's something that we won't really cover today, but it's a version of refining our fuels. Now, carbon neutral refers to the recycling of carbon. The carbon is released as greenhouse gas, CO2, and is approximately the same amount absorbed during the process of fuel creation. So this is something you may need to talk about. So let's just say we have energy, and that energy from the sun goes into photosynthesis. So we have energy from the sun goes into photosynthesis. That photosynthesis and that plant is then used to produce biofuel. That biofuel production probably produces a little bit of CO2. Naturally, it has to. We have to use facilities that use energy. We produce a little bit of CO2 when we produce our biofuel. We then have to transport our biofuel. That's probably going to release some CO2 as well. We then use our biofuel, and our biofuel does produce CO2. That's the natural fact of it. However, if we say that that energy that we produced, and I think that sum was meant to come up at the start, apologies, I don't know why that all came up at the end, but that energy that was absorbed at the start, if that energy production also absorbed the same amount of CO2 that was absorbed, that was produced throughout the process of creating it, well, then we can say that it's carbon neutral, because the plant absorbs so much CO2 that when we did produce CO2 from the products of that plant, it doesn't really matter, because we're pretty happy that we've already absorbed that CO2, so therefore it's pretty carbon neutral. What we have used, we have then sent back out, if we think of it like that. What's also really cool about fuels is their different features. So we have features such as renewability, which we've discussed. Energy content. So general rule is fossil fuels are greater than biofuels, but obviously you've got to think about the different types. So like a natural gas is going to have less energy than a biodiesel, because biodiesel just has so many more bonds. That's just natural. But if you compared biodiesel with petrodiesel or petrol, they're going to have way more of the fossil fuel. You've got to compare like things with like things. The fuel structure. So most biofuels are polar, most fossil fuels are non-polar. What does that then mean? Well, then it means, importantly, for things like viscosity and interactions, you have differences. So the viscosity refers to the thickness and the resistance to flow. So the resistance to flow, if you have more bonds, you're polar, you've got intermolecular bonds of hydrogen bonds, you've got dipole-dipole interaction, you've got dispersion forces, you've got all three of them in a biofuel. Because you're polar and you have oxygens present in your molecule, they usually are, you therefore are going to be thicker. That's the reality. You're not going to flow as well. You're just not going to flow. You're going to be thick. When you cool it down, it's going to be clogging up fuel lines. It's not going to be all that useful. Whereas our fossil fuels are non-polar. Fossil fuels being non-polar means they only really have dispersion forces. They're pretty weak. And given how weak they are, they sort of just, they sort of just do their thing. So given that fossil fuels are non-polar, they don't have thickness, they flow, they're like water, they don't resist flow, and therefore they're more useful in colder environments. They're more useful in general. Interaction, so again, known as hydroscopicity, or I can never say it properly, is what it is. But essentially, if you're polar, you're going to absorb water, so therefore biofuels are going to absorb water. Boiling points, more bonds, higher boiling point. That means biofuels are more likely to be sort of liquids at room temperatures, whereas fossil fuels, smaller fossil fuels, like biogas and even things up to like butane and even borderline pentane, at room temperatures, they're nearly a gas. Whereas if you look at something like butanol, for example, so butanol there might be a way of producing that as biofuel. Usually there is. If you have something like butanol is going to be a liquid because it has a polar aspect of it, and therefore it's going to have a much higher boiling point than its comparator. And combustible products, fossil fuels are actually worse in this aspect. Fossil fuels usually contain really lots of particulates. They contain a couple of random little atoms here and there just because they've had years of compression underground. And these can be damaging, and they're usually more damaging in their greenhouse gas production as well. Now, what's also really important is this is one of these question types that I really want you to know. So we do have these comparison questions. These do come up pretty commonly. So comparison questions essentially want you to compare two concepts and see if you can discuss both of them without just saying, oh, this is the better one. Or they want you to say why and talk about both. So here's a really common example. Now, what's really important is this question is less likely to come up now. The emphasis on these types of questions have been significantly reduced. That is, I cannot deny that. However, they're still going to come up, and I still think there will be one or two comparison questions on your exam, no matter what, because there was such a high proportion of them. They can't get rid of all of them at once. That's the way it is. There will be comparison questions, and there is a distinct way to answer them. So, example here is they want you to talk about the suitability of biodiesel versus petrodiesel as a fuel in cold climates. This would be a terrible response, and one that this would be a 2-mark question, might get you 1. Might. It'd say petrodiesel only experiences weak dispersion, force attractions, thus it has a low cloud point, making it more suitable to use at room temperature. Now, don't worry about cloud point, that's not part of the study design anymore, but I just want you to understand that this here just doesn't discuss anything to do with biodiesel. Where is the mention of biodiesel? There's no mention of biodiesel, whereas this one here mentions both. While biodiesel experiences dipole-dipole attractions, petrodiesel only experiences weaker dispersion forces. Thus, petrodiesel has a lower cloud point than biodiesel. Just saying than biodiesel, that's all you needed there, making it a more suitable fuel. Once again, don't worry about cloud point. You could use something such as viscosity here. You could literally just plug in viscosity into the cloud point. Cloud point's it's just not mentioned in the study design anymore, so it's something that we're not going to discuss. Viscosity is. You do need to know about viscosity, so you could just plug in viscosity into the cloud point here and literally just say viscos has a lower viscosity than biodiesel. So saying what is underlined here and bolded, that gives you your 2 marks. This would struggle to even get a mark. If the examiner's feeling nice, they might give you a mark. If not, you probably won't get a mark here. This will get you 2 marks. So it's really important you understand those distinct differences between those two. Now, how do we release energy from fuels? Well, we essentially set it on fire. But we call this combustion. That is literally what we do with fuels. We pretty much set them on fire, just like that. But we call this combustion. So, combustion is really interesting. So combustion comes in 2 forms. There's complete and incomplete. We'll talk about complete first. Complete combustion is when we essentially react a hydrocarbon or a fuel with oxygen. And what that does is it produces carbon dioxide and water and energy, essentially. So an example here is we have ethanol. So that's ethanol there in a liquid form. Ethanol is reacted with oxygen. This has been balanced. It produces CO2 and H2O. And what's really important about this is that we must always balance. So as you can see here, if I look at my reactants, I have 2 carbons. I have 6 hydrogens. I have 6 hydrogens because I added the 3 out the front here. I now have 6. I have 7 oxygens because I have 1 here and I have 6 here. I have 4 here and I have 3 there. I have 7 oxygens. You need to balance. You need to make sure you balance all your equations particularly combustion equations as you go through. Now, what about incomplete combustion? This is something that comes up and it is a skill you need to know. So before we looked at these, we looked at, so this is a combustion reaction. This would be for, what is that? Heptane. So this is heptane here. I was just trying to remember which wording that is. This is heptane. So heptane would be a version of petrol. It's not the octane version, but it would be a version. As you can see here, I've balanced this out, and that's how it works. However, what if I want to do incomplete combustion? Well, I don't do CO2. I actually do carbon monoxide. Now, really key point with this, and you will learn about carbon monoxide. Carbon monoxide is a poisonous molecule. Carbon monoxide is produced when we are combusting a fuel, but there is insufficient oxygen. So there's still oxygen present, but there is insufficient oxygen. So there isn't enough to actually get this to work. So essentially what that means is we're trying to combust a fuel, we just haven't filtered enough. It's why cars have filters. So example, you know, a four-wheel drive. So imagine a four-wheel drive. Imagine like a big Land Cruiser or something. I'm from the country, that's why I love these things. They get a big Land Cruiser. A big Land Cruiser, and you know with a Land Cruiser they have, usually it's in black, it's like a safari one, and it's a big sort of plastic tube that runs up the side of the windscreen and then has like an opening that opens out forward. We call that a snorkel. Funny enough, it's called a snorkel. And if you think about it, what is a snorkel used in real life? So we use a snorkel when we're underwater. Why do we use it? We use it to breathe. We use it to have an aspect that is capable of being above the water, and it is where the oxygen is. In a four-wheel drive, it does the exact same thing. So if you think about someone who goes four-wheel driving and they drive their car through puddles, and when I say puddles, I'm talking about bodies of water that probably go up to your waist. When the car goes into that, the front of the car and the grille of the car, the front of the car, goes under the water. When it goes under the water, that grille is purely there to allow oxygen into the system. It is purely there to allow air to flow into the motor and combust the fuel. But if you don't have oxygen going in, what's going to happen? You start to do incomplete combustion, you produce carbon monoxide, which is not good for your engine, and eventually you just won't be able to combust fuel. You will have no oxygen there, combustion will stop, your engine will drop out, you'll probably stall your car, your engine will drop out, and your car will stop. And where are you? You're in the middle of a puddle and you're stuck. Nothing you can do. So essentially, a snorkel on a car is the exact same thing. It acts as ventilation. It sits much higher up because it sits above the windscreen. It brings air into the motor. Really, really, really important. And it's a very practical example of it. You need oxygen to have combustion. And so when you have insufficient oxygen, as you can see here, you produce carbon monoxide. Now, carbon monoxide on the other hand, because I got sidetracked just talking about ventilation, carbon monoxide on the other hand is a very poisonous molecule. So carbon monoxide is known as the silent killer. About 15, 20 years ago, there was a really big drive for everyone to change their heaters, and it's still going on today. They're still driving it today. They're finding more heaters that do it. Heaters with insufficient ventilation, even if they're working off an electricity base, not a fuel base, they still require ventilation. Don't stress about that too much. But essentially, think of old heaters, and we'll think about gas heaters. So gas heaters, they bring in gas, that's their fuel, they combust. Using oxygen, they produce heat, and that heat is released as a heater. What we found is a lot of old heaters had terrible ventilation, terrible ventilation, and they didn't have sufficient oxygen. So if you made them run high enough, they wouldn't produce any carbon dioxide. They produce carbon monoxide. Carbon monoxide is a colorless, odorless gas. There's no color, there's no odor. It just looks like gas. You can't even see it. It's poisonous. It's extremely poisonous. In small quantities in a room, if you breathe it in enough, you will die. That is the reality of it. It preferentially binds to hemoglobin in the blood, and hemoglobin is meant to carry oxygen around. Well, when that's preferentially bound to it, your blood can't carry oxygen, so you essentially suffocate in the air. You essentially suffocate while being not underwater. Very, very alarming image. Please don't think about that too much. But essentially, what I'm trying to say here is that carbon monoxide is really dangerous. So we don't want this to happen. And it's a practical example you will talk about. It does come up. They want you to talk about how carbon monoxide is poisonous and it is not wanted. So we need to have sufficient ventilation on things to allow the gas to react properly. And it's a practical application of complete versus incomplete combustion. Incomplete combustion produces carbon monoxide. It's the only difference. Complete combustion produces carbon dioxide. Now, also what's really important about this, notice how in this equation here, I've doubled this. That's because this would have been a half number. If I had this as 1, this would have been 15 over 2, which is, 7.5. This would have been 7.5. You cannot have half a molecule. Please, please, please never put a fraction or a decimal place when you're balancing out an equation. Even if your teacher says, okay, when you move to university level, it's not. And at VCE level, they will accept it at times, and there will be times where they don't. But if you move forward with chemistry, or you take anything out of chemistry, that makes no sense. It's like when you do a survey and someone says, oh, I have 2.5 pets. What does 2.5 pets mean? You can't have half a pet, you can't have half a dog. It makes no sense. It's the same with molecules. You can't have half a molecule, so please do not have this as 1, which is no number, and have this as 15 over 2. Please, please do not do that. That is the worst thing you can do. Or saying 7.5 is the worst thing you can do. Please do not do that. Even if your teacher says, oh, I don't mind, I'll accept it because you've balanced it. It's not acceptable in my eyes, and it's not acceptable at a level above VCE, which is what you should be aiming. You should be always aiming to go as high as you can. So please make sure you do not do fractions or decimals. So it's there, that's incomplete combustion. So then we need to look at something called a concept called enthalpy. So enthalpy is a really interesting concept, and enthalpy is where we get our thermochemistry really kick-started. So enthalpy is signified by a delta H, so a triangle H, that means delta. Enthalpy change means energy change. And what we mean by that when we put it on a chemical equation is what is the energy change within the system? Now there's 2 distinct ways of looking at this. There is a system that releases energy, and there is a system that absorbs energy. So when I go for a run, I go through aerobic respiration and I release energy. Now, when not me, or when a plant is sitting there, for example, so if I grab a plant, there's a plant just over to my left, a plant that sits there, a plant goes through photosynthesis and it produces glucose. It produces oxygen, and it does that by absorbing energy from the sun. So it goes through an endothermic reaction. So exo means exiting energy, exothermic, and then endothermic is just the opposite, it absorbs energy. So a delta H is placed at the end of every thermochemical equation, and it requires a symbol. If it is an exothermic reaction, this is negative. If it is an endothermic reaction, this is positive. And really important, it needs a positive sign. You can't just write the number and expect everyone to know it's positive like you do in normal maths. It has to have a positive sign. Now, delta HC is utilized for molar values. Please don't worry about this. You'll learn this in more detail in your topic, but essentially this is just like standard values. This doesn't have a symbol because it's just like the standard value for something. It's like a known value, so don't worry about that. So let's have a look at our 2 types of reactions. We have an exothermic reaction. Now, an exothermic reaction essentially looks like this. You have your energy of your reactants, and then you have a reaction and energy is released, and your energy of your products is a lot less because all this energy here has been released or it's been lost from the system. If you think about it, this is a fuel. When you combust a fuel, you have lots of energy, you then combust it, the energy goes into the car motor and does its thing, and therefore the products that are left have very little energy left, but you've already done what you wanted with that energy. The energy has been moved off and transferred elsewhere. And we like to think of it like this. This is our equation for delta H. It's our products take our reactants. Because our reactants have more energy than our products, we're going to end up with a negative value. So delta H is always less than 0 if it's an exothermic reaction. Now for endothermic reactions, it's the opposite. Because the products here, so these are the products, have more energy than the reactants, because there's more energy here, the products take the reactants, it'll be a positive number, so you need to put a positive symbol out the front, and you get delta H is greater than 0. Now, this is a really, really good question. I really like this question here. I want you to have a think about this. This is probably a little bit beyond where you're at the moment, but I want you to have a quick think. So take your time, pause. It might be beyond the scope of where we're at, and that's okay. If you don't understand, I'll explain it after. So 3, 2, 1, pause. and hopefully you're back. Now, hopefully you took maybe 1 or 2 minutes doing this, and if you had no idea, that's okay. If you got an answer, awesome. So what we've got here is the combustion of methane, and methane, as you can see here, produces this much energy per mole. Now we will discuss that in a little bit more detail, but really importantly, it's negative, so it's exothermic. And a plausible interpretation of this thermochemical equation is, so this is how much energy it produces per mole of this. Each of these answers here is really interesting. So it says 800 kilojoules is used to break the existing bonds of CO2, CH4, so the methane, but not in O2, as O2 is a pure element, and this much energy is released. Well, no, that O2 isn't released as a product, so the O2 must be broken down to bind onto other things, so no. So that's what I wanted you to get from that answer. The rest of it might have been a bit confusing, but understanding that the O2 isn't released as O2, it has to be broken down. So therefore, A is wrong. B, 450 kilojoules of mole is released when the bonds are broken, another 439 moles released when the bonds are formed. We don't produce energy when we form bonds. That makes no sense. We only produce it when we break them. So B is wrong. We would actually absorb. C, no energy is used to break existing bonds because the products are lower in energy than the reactants. Well, that makes sense and is released when the products are formed. This is not released when the products are formed, but I think the most important thing here is no energy is used to break existing bonds. Remember that with a fuel, we need to combust it. We need to spark it. We need to give it a little bit of energy to release loads. So therefore, C is wrong. And if you felt like C was the answer, that's okay. We haven't really discussed that whole sparking aspect, but it's something you will discuss throughout learning this topic in more detail. And it's one of those things that, as you can see, that is why C is wrong. And then D, I'm kind of left with it. I think D has to be my answer, but we can go through it. It says this much energy is used to break the existing bonds. Well, that's a lot of energy absorbed, but we're releasing energy. And then it says this much energy is released when the bonds are formed to produce CO2 and H2O. Again, this statement I don't love because releasing energy when you're forming bonds doesn't really make sense. It's sort of released at a different time. Although it all happens at once, it's kind of different aspects, but they've sort of merged into one, so it's okay. But if you look at this, it says it breaks the bonds of CO4 and O2, which is correct. It needed that. And this is the amount of energy released. If I took this number away from this number, I would end up with this. And therefore, D is my answer. So that is why D there is my answer. This is a really, really good question. It's a great question as you get further in as well to sort of come back to and just make sure you're on the right track. So we just saw a thermochemical equation. Let's just discuss them very quickly. Thermochemical equations look like this. So as you can see, I've got a balanced equation and I have a delta H in the end with a negative symbol at the front, and it's usually in kilojoules per mole. You always go to that if you can. If you cannot, you go to grams, but you try and do kilojoules per mole. This is the chemical equation. That's the enthalpy change. You only need to put this aspect on if they ask for a thermochemical reaction. If they ask for a chemical reaction, this is not necessary. You do not need to put the enthalpy change value. You only do that if it says thermochemical reaction. Enthalpy change is measured in the units of kilojoules per mole, but also in kilojoules per gram. The delta H with changes with the, I added as in there, I was trying to think of something else, with the coefficient of fuel changes. So if I double this, so as I've said, I've doubled this, or this should say with changes. Yeah, I don't know. Anyway, I butchered that English. As you can see, I've doubled this equation, so I've doubled my delta H. Again, it's still negative, but I've doubled it because I've doubled this out the front. So it's always the fuel you look at. You don't look at everything else. Don't worry about the oxygen. Don't worry about the H2O and the CO2. You only look at the fuel. This is the fuel. Therefore, that's where the energy comes from. There's also some other tricks here. As you can see here, we already discussed, we multiply the coefficient, you multiply the delta H, no matter what. If I multiply my coefficients by 3, so again here, this is what we're producing. This is the fuel we are producing. So we work off the glucose here. So this is producing glucose. That's why it's positive, but that's the fuel. Essentially, we're producing a fuel here. That's why we're absorbing. We're not combusting a fuel. So because we're producing a fuel, we look at the fuel. It's been doubled. Therefore, I need to double this, and I have. If we want to reverse the equation, we have to flip the sign. So as you can see here, we have CO2 plus H2O goes to our glucose. So again, this is photosynthesis. Then we flipped it around. This time we're going through aerobic respiration. And therefore, because we flipped it, we flipped the sign. So that's how you go about that. Now, again, this is a really, really good question. I'm going to go through it pretty quickly. I'm not going to spend a lot of time on it, but you guys at home, guys and girls, can take your time and have a go at this question. So please feel free to pause and have a go at this question. It's a solid 3 or 4 minute question. It's worth 5 marks. You can take 5 minutes if you want, but I want you to have a go at it. If you struggle with it, that's okay. I'm going to go through the answers pretty detailed. It's a pretty detailed question. 3, 2, 1, pause, and hopefully you're back. So let's have a look at this question and let's go through the answers. So with this question here, you have, by using enthalpy change formation, we can calculate the values of delta H from any reaction. Given the reaction of dinitric tetrachloride, whatever these are, and ozone, reaction forming these species, respectively, for their elements and their delta H's are below. So what it wants is you to produce this from these 3. So you last year would have done adding together equations to get what you want. Now we're going to work with our delta H's. So the best way to do it is to label 1, 2, 3. So first of all, we have this equation here, and we flipped it. Why did I flip it? I want this, which was on the right side, on the left side. So wanting it on the left side, I flipped this equation. I flipped this delta H. 2. I wanted this N2 gas to be a singular. Sorry, this N2O gas to be a singular. Now, I know that this breaks a lot of rules and rules that I mentioned before, but for the meantime, we're going to get rid of this oxygen. This oxygen isn't going to be part of my final product, so I'm happy for it to be a half just for now. Just for now, I'm happy to be a half. In my final answer, I wouldn't be having a half number. Now my third one, again, I'm going to do the same thing. I'm going to half it because I want to get rid of this O3. I want to have this O3 as a 1, so I have halved it. Again, I end up with a 1.5, which I don't like, but for now it's okay because all I need to do is get everything in the form I want it. And again, I've halved my delta H. Now what I do is I add them together. So I add all 3 of these together. So by adding them together, these 2, that is on the left, that's on the right, there's 1 each, I get rid of them. There is 1.5 and a half, which is 2 on the left, and there's 2 on the right, I get rid of it. I'm left with what I want. I've got this on the left, I've got these 2 on the right, which add up, and I just need to add these delta H's. So I add the negative to that, which would essentially make this number smaller. It would make this number 70.5, and then I add 70.5 to 142.7. And essentially, as you can see there, I get 213 kilojoules per mole. So, difficult question. Please do not get this wrong. This is a difficult question, but it's something that you can start to see the concepts we just discussed getting integrated in together. So, what's also really cool about this is that you have in your data booklet a whole bunch of heat of combustions. So molar, these are delta HCs, that's why they have no symbol, but they're all combustion. So they're all, when you put them on an equation, they're all going to be negative because you're going to, you're releasing energy. But because they're delta HCs and they're standards, they don't have a symbol in the book. But as you can see here, there's a lot of gas. There is a lot of gas. A lot of these fuels we work with are gas. And as you can see, that example from earlier I discussed like methane versus methanol, or like ethane versus ethanol. Notice how these ones, these fossil fuels that don't have a polar aspect, they're all a gas because they've got a really low boiling point. Whereas these ones that have a polar aspect and are biofuels, more likely to be biofuels, do have a polar aspect and therefore they've got a much higher boiling point, and therefore they are a liquid initially. But as you can see here, we've got our gas, we've got a lot of gases. So what do we do if we have to work with them? Well, we use our universal gas equation. Now, this is something that you will have worked with already. You will have worked with this in year 11 or year 10, no matter just when you did unit 1-2 chemistry. Really important, just remember the values. So P is pressure in kilopascals, V is volume in liters, N is your moles, R is your ideal gas constant, which is 8.31, and T is your temperature in kelvins. Remember, kelvins, you have to add 273. So you add 273 to degrees Celsius and you get your kelvins. Remember, with kilopascals, you need to and this is something you may not have discussed last year, you need to convert. You will find the conversion values in your data booklet. So if I scroll down, right here, page 6, figure 5, unit conversion, 100 kilopascals is equal to 750 mils per mils of mercury, or 0.987 atmospheres. So that's mils of mercury, by the way. Hg is mercury, and that's mils. And then this is atmospheres. If you're given your pressure value in one of these, you need to convert to your kilopascals. So really important, you do need to know how to convert, and that's something that comes up. Same with volume. So volume needs to be in liters. So if you've got mils, make sure you convert it to liters, and then moles. If you're given something in grams, you need to convert it to moles, etc., so forth. So just make sure you do all of those aspects, and then you utilize these within your question. And this is a really common, this comes up all the time. There will be numerous marks on the exam for this equation. Please know this equation. Please know how to use this equation. It's really important. So practice question, a 250 ml compressed air container contains CO2 stored at 10.2 atmospheres at room temperature. Find the mass of CO2 in the canister. Have a go at this question. It should be pretty straightforward. You just need to do some conversion and then use your PV equals nRT. It should take you no more than 2-3 minutes. I'll give you your time now. 3, 2, 1, pause. Again. Hopefully, you're back. So, hopefully you've gone through and done that question there, and hopefully you didn't have any troubles with it, but we'll go through the answers. I did these beforehand just to make sure that I didn't have to write on the screen and have my messy handwriting on there. We have PV equals nRT. I'm going to convert that into, I want to find moles, so I'm going to find mass, so I need to find the moles to then find the mass. So I'm going to find the moles equals PV over RT, because I divided out my RT. I converted my pressure to 1033.4. Now, how did I do that? This is a really interesting aspect. You take this number, the 10.2. I should have probably put this down the page as well. I take the 10.2 and I divide it by 0.987. So I divide this number by 0.987. It's probably going to come out as like 10.3. It's not going to make the number all that different. It's going to be very, very similar. And then I multiply that number by 100, because there's 100 kilopascals per one of this. So 100 kilopascals, multiply this by 100 kilopascals, and I would end up with this here. So my answer when I divided this by 0.987 would have been like 10.334. I'm pretty sure that's what, because my decimal place would have moved. So my answer here would have been 10.334, times it by 100, and I get 1,033.4 kilopascals. My volume needs to be in liters, so it's going to be 0.25 because there's 1,000 mil in a liter, and my Kelvin is plus 273, so plus 273 is 298, as you can see here, 298. Then I go to here and I go, all right, what have I got here? I've got my equation, so I do moles equals pressure by volume divided by pressure, my constant, 8.31, by my temperature. And I end up with 0.104 moles. I should have written moles there. Apologies. Mole. All right. 0.104 mole. Definitely always put units on. I do apologize if I've got units there. Then from there, I just need to find the mass. So I do my mass equals moles times molar mass. So my moles 0.104 and my molar mass of CO2, which is a 12 carbon and 216 oxygens, which is 32 plus 12 is 44. So 44, and you get an answer of 4.59 grams. So again, units are really important. You need to make sure you put units on everything. Don't make the mistake like I did and forget units there. Units need to be on everything. All right. So in many cases, we'll be given the universal gas equation in question, and we'll be told the conditions are SLC. So what are SLC conditions? I hope you remember this from last year. If you don't, that's okay. It's 25 degrees Celsius or, 298 Kelvin. It's 100 kilopascals of pressure. And if you're working with a liquid, which obviously you wouldn't be working with the universal gas equation in that case, but if you are working with a liquid and you're told SLC, it's a 1 molar concentration. So it's an aqueous solution that is 1 molar in concentration. So they're your aspects of SLC. Now, you might also see other things like STP. Now, in older exams, STP was what we used to use instead of SLC. Please ignore those. If you do those questions and you find you're getting the wrong answer, look at how they got the answer. They'll be using different values because STP was different. We now use SLC. So you might actually be getting the correct answer, by our standards today, but you're getting the wrong answer by their standards back then. But don't worry about that. You want to use SLC. Now, how do we go about these questions? So if I'm told a universal gas question and I know I want to find either the volume or the moles, and I'm told that I'm at SLC, well, we can go the long way and we can put, 298 Kelvin, 100 kilopascals in and write out the whole thing. Or we can use what we call the molar volume equation. Now, the molar volume equation essentially says that the volume equals the moles times the molar volume. And molar volume is 24.8. So essentially, 24.8 is the combination of this number here with this number here and that 8.31 constant. And what we're left with, because they stay the same, when we're at SLC, they are the same. They're always going to be 298 Kelvin, 100 kilopascals, and 8.31 as the standard. Combine those three numbers and simplify my equation. Now I'm just left with volume because I've removed the pressure from this side, and I'm left with moles by my molar volume, which is the combination of R, T, and P. So R, T, and P, and I get V equals N by Vm, which is 24.8. Now you'll find this equation is in your data booklet. So if I go to my data booklet and I scroll up, you'll find there's your 24.8. I actually think the equation is in here. No, the equation's in here. There you go. There's your equation. So moles equals V over Vm. And you'll find that in your data booklet, you're given both the R value and the Vm value. They're both in there. So you can always come back to it and find that if you need. All right. So let's move on now into some food chem. So food chem is really interesting because food chem does actually, I really like the way they've led this on. I really like the way they've made this lead on from sort of fuels and thermochem, because food used to be the end of the year, but it made sense to be now because food is essentially the fuel of the human body. We understand that it's our primary source of energy. We have three main macromolecules in which we obtain energy from: carbohydrates, so simply just our sugars. So sugars are the lay term. You in chemistry will use carbohydrates. That is the scientific term. You are in a science subject, use carbohydrates. You also have proteins, and you have fats. So fats, we can also refer to as lipids. Again, fats is the lay term, but it's more interchangeable. We do use the word fats a bit in science talk. So you can sort of use both. Lipids sounds more professional, but both of them work. From here, in order to utilize these, we must first break them down from food source into monomers. So monomers, this is a very biology topic, but essentially monomers are the individual units. So for a protein, the individual units are an amino acid, or for carbohydrates, it's a glucose molecule. And then the polymers are just like the bigger complex molecules. So if you had an enzyme or a full protein enzyme produced from amino acids, or you had like starch. Starch is lots of glucoses put together into a big polymer, and we call that starch when we eat it from, plant food. The pathway of food breakdown to storage is a really big aspect of this, but it's also not covered in this area of study. So you don't need to know this until Unit 4 area of study 2. It's a bit in both. It's really important. It comes up in Unit 4. So you do need to know, from the eating of your food to your running of a marathon, what happens with your food, where does it go, how do we bond it together, then how do we break it down, what forms do we put it in, why do we put it in those forms, why do we break it down, etc. It's all got to do with reaction pathways. It's something that is covered in Unit 4. So therefore, it makes sense to split this topic up. At the same time, it did make more sense when it was together, because you sort of went through what we go through today and then you went into that reaction bit. Now what you're going to do is go through what we go through today and then come back to it later on. But we're just going to go through very briefly what each of the macromolecules are. We may go into a little bit too much detail for Unit 3 Area Study 1, but all the detail that we cover today is examinable at the end of the year. So don't stress. So we'll start with carbohydrates. Again, in non-science terms, we call them sugars. You're going to call them carbohydrates from now on. They're the primary energy source of the body. They're made up of monomers called monosaccharides, or more commonly called glucose. You can use either of those terms. That is glucose, it's C6H12O6. Polymers are polysaccharides. Makes sense. Mono means one, poly means many. And they vary depending on the location of creation. So what I mean by that is that, if I go through, so polymers include starch, which is found in plants, cellulose, which is also found in plants, but it acts as fiber. Now, it acts as fiber because it's a beta glucose, and we do not have the enzyme to break down beta glucose. I'll explain in a second. And then glycogen. Glycogen is how we store it in the human body. These are very similar, starch and glycogen, very, very similar, but there are slight differences. Alpha glucose is the form of glucose we use in the body. Now, alpha glucose is where the C1OH groups, this is C1, this is our first carbon. We refer to this as our C1. You'll learn more about this in organic chem, or you may already know this from last year. This is really a year 12 sort of, unit 3-4 sort of topic. But that C1, essentially, it's the OH group faces down. And essentially what that means is that spatially that faces down. It goes down below the molecule. Obviously, it depends on which way the molecule's facing, but we're going to say it's down. In a beta glucose, that faces up. So as you can see here, this bonds to your next glucose. So it bonds to your next glucose. So if it's down, your glucose should go like this. Your glycogen should go like that. That's how your bond should look. But notice how in cellulose, it goes up. So therefore, you go up with your bond. Therefore, it's unable to be broken down by the body. It's just a very, very tiny difference that makes the enzyme not be able to break it down, and that's why we work with alpha glucose. Proteins. So proteins are the building blocks of life. For those of you who go to gym or love the gym, or you will have heard about protein shakes and so forth, proteins are really interesting and complex molecule in terms of that, and it's really complex in the body. The body can only take in a certain amount of protein, but it also can alter that by how much you work out, how much you do things. Therefore, you'll find that as you go through and you do things, your body can absorb more protein. That's why people take protein shakes. There's also limits to how much muscle mass you can gain at times because of protein, etc. It's a very, very complex and interesting side of science. But proteins are found in everything. They are the building blocks of life. And that's why even when you're having a protein shake, sometimes your body just uses the protein elsewhere, because protein is everywhere in your body. They form important enzymes to molecule carriers, such as like hemoglobin carrying oxygen in the blood, to structural components of your body. These consist of alpha amino acids. Again, alpha, we use them in the body. These are the monomers. 20 exist in the body. 11 of these are non-essential, so they can be created by the body when we need, and 9 are essential, so we must possess these in our diet. They're in lots of things, but we must eat them in our diet. All alpha amino acids are found on page 14, 15 of the data booklet. So if I go to my data booklet and I go right down to the bottom, I think it's right at the end, you can see here, these are all the essential amino acids. Now, you do not need to know which of these are, essential or non-essential. Sorry, these are all the alpha amino acids. You do not need to know which of these are essential or non-essential. These are just the alpha ones. You just need to know that these are alpha amino acids. All alpha amino acids have a general structure that looks like this, which means you have a central carbon connected to the 4 groups. Now, the 4 groups are an amino group, given it's an amino, and then an acid group, so carboxylic acid, so amino acid, makes sense. Then you have a hydrogen, just a singular hydrogen, and then you have a side chain. Now, R refers to a side chain. It means there's something there that's different. So in all of these, if you notice, there's your central carbon, there's your side chain. There's your central carbon, there's your side chain. There's your central carbon, there's your side chain, etc. They all are very similar. They all just have a different side chain. That's what differentiates them. Because we have so many amino acids, the order in which you put them together to form a protein is important. Again, you don't need to know all the bonding and so forth yet. That comes in Unit 4. Then we have fats. So fats and lipids, specifically triglycerides, are made up of 3 fatty acids and a glycerol. Despite these components being referred to as monomers, they technically don't actually meet the criteria. We will refer to them as monomers, but they technically are not, if you go into technicalities. But don't stress about that. This is essentially what it looks like. It's really long fatty acid chains with an ester bond, and that ester bond connects to a glycerol, which is essentially, if you cut it down here, it's a glycerol, so these would become hydroxides. These become like alcohols. So you have 3 alcohols coming off a 3 carbon chain, 3 hydroxides. Fats are deeply complex molecules, much like carbohydrate proteins, and these will be further unpacked in Unit 4, Area Study 1. So these are really complex, and again, they come up, we've already discussed them as part of our transesterification reaction, as part of producing a biofuel. These are really complex, and that's why, for the sake of it, lipids are only used as a fuel source as like, when I'm sitting here, I'm not using a lot of energy. I'm actually using fats. You use glucose when you are going for a run. You will use some fat, but you use glucose because you're running and you need energy quick. So when you're doing an exercise, you need energy quick. You then therefore use more sugars, you use more glucose. They produce energy a lot quicker. Fats produce more energy, but are really slow. So when you're not using a lot of energy, your body sort of preserves carbohydrates and uses fats. Really interesting concept. But this is what's most important, is this here. Now, this is found in your data book, but again, it's figure 13. So if I scroll up and find figure 13, there it is. Just went past it. I passed it again. There. Figure 13. Energy content of food groups. What you want to know for this topic is that each of these molecules have different energy content per gram. Now, we work with per gram in food because food is never pure, so you can't use moles. When you look at the back of a food packet, it'll tell you how much, carbohydrate, how much protein, how much fat and oil, etc. is in it. You'll find that each of those produce this much energy per combustion. So when I say this much energy, it produces way more than this, but this is how much we can actually utilize in our body. It's what is usable energy when we combust it in the body. So we like to also think of that when we combust it and we look at our when we combust it to test how much energy is in there. So when we combust these, we find this is how much energy we produce from each. You'll be given a question where you're given a food, you're given how much of each component macromolecule is there, and you'll be asked to figure out how much energy has been produced. You utilize this graphic or this table here. This is really fun. Now, pushing through, we're going to push through these last 20 slides pretty quickly. Calorimetry, this used to be a massive part of Unit 4 of Study 2. It's now been moved here. It's not as big now, it's a lot smaller, but I am just going to go through it very briefly. Calorimetry is used to measure the energy change in a substance when it undergoes a reaction. So generally in a substance with unknown or variable molar mass, so generally a food. We generally use food. It comes in two forms, bomb and solution. Bomb is the most common. The basic methodology of calorimetry is that inside the calorimeter, we call it calorimeter, so it's just what the machine is called, there's a known volume of water. So you have a known volume of water, a sample is put inside and it reacts and it releases energy, and then you just, it exchanges the energy into the water and you measure the temperature rise in the water. So this is what bomb calorimetry looks like. You have this little bomb, you have a battery that ignites, and the bomb is essentially the food. And as it ignites, we essentially heat up the water around it, and then we look at the thermometer and see how much the water changes. Very similar to solution. Solution, on the other hand, is you sort of put everything straight into the known volume of water. So you sort of make it like an aqueous solution, and then you mix it. And then as you mix it, because you've put everything in there together, it should sort of react, and your whole system should heat up, and therefore you measure the temperature change again. Now, there are some equations for this. I don't want to go through this in super detail. I don't want you to come out of here going, oh, I know all about calorimetry. Calorimetry, not a big deal. What I want you to know from this is that calorimeters require calibration prior to use. And so we need to calculate what we call a calibration factor. Now, there are a few equations here. I just want you to have seen these equations. You need to do questions for these to know how they work. And that's why I'm not stressed about you knowing all the details about it today. But there are two very distinct equations. There is this equation here, which is all about energy. So the energy in joules is produced from electricity. Now, you might have said, oh, there's no electricity here. Well, when we calibrate our calorimeter, we apply some electricity to the environment. And when we apply electricity, if we apply it for a certain amount of time, at a certain amount of volts and a certain amount of amps, we know exactly how much energy we've put into the system. We know exactly. So then we can determine how much energy, we can determine the temperature rise, and we know how much energy we put in there, and we can sort of determine the calibration factor. So for this much energy, I get this much temperature rise. All right, now I'll put a food in there, and I got this temperature rise. Well, now I can work backwards and figure out how much energy was released. So as you can see here, the calibration factor equals that energy divided by delta T. So you technically can write this equation like this. Your voltage, your current by your time in seconds divided by the temperature change. So delta T, remember delta means change. Remember in enthalpy, delta H meant change in enthalpy. This is delta T, so this is change in temperature. And really important, this needs to be in kelvins. You need to be working in kelvins at this point. You can work with degrees Celsius. You will find sometimes they do. We generally like to work with kelvins though. So as you can see here, your calibration factor should be joules per Kelvin. So joules per Kelvin. So really important, these two equations work together closely and you get a calibration factor. You can then use that calibration factor to determine how much energy has been released from the food. We're not going to go through that today, but I just want you to see these two equations and know that they exist and know that you're going to need to utilize them, and that when they do come up, when you start learning this topic, maybe in a couple of weeks, it'll probably be like, I'd say maybe 3 or 4 weeks in to your semester, you'll start to be like, all right, I know I've seen these before. I kind of get what calorimeters are. I'm going to learn this in more detail. It should make more sense off the bat. But then you also need another equation sometimes, and that other equation that you need, and I went backwards, is your specific heat capacity of water equation. Now, this should be a revision. I've put a practice question in because I just wanted to make sure that you remembered how we use it. But remember that it's the amount of thermal energy required to heat up 1 gram of water by 1 degrees, which is 4.18 joules. Really important. 1 gram of water, not 1 mil. 1 mil of water is not 1 gram. Converting wise, going from mils to grams, it's 0.997. It's not 1. It's very close to 1, but it's not 1. So please remember that when you're working with specific heat capacity, you need to have water in grams, not in mils. So we can use the specific heat capacity of water to estimate the approximate amount of energy released as heat in a combustion. This is particularly useful in food chemistry, as we're discussing now. Your equation looks like this. Q equals mc delta T. I hope you remember this. It's actually a really good equation, really good to work with. But you've got energy in joules, your mass in grams, your specific heat capacity. It's technically in joules per gram per Kelvin. Don't worry about it. It's just going to be 4.18. And then your delta T. Now, you can utilize this equation for other things other than water, but you need to be told this. If you're not told this, you would be told everything else and you would be figuring out what this is. The question might be, figure out what the specific heat capacity of methane is, or methanol is, something else. You might be working with something else. Don't worry about it. You essentially will most of the time be working with water, and if you're not working with water, you will be told what the specific heat capacity of the substance you are working with is. It will be in the question, so you will work with it. Nonetheless, you most of the time work with water. The change of temperature can either be Kelvin or degrees. It doesn't really matter, because if you go from 25 to 30 degrees, there's a 5 degrees Celsius difference. If I go from 298 to 303 Kelvin, which was 25 to 30 degrees Celsius, there's the same difference. There's 5 Kelvin. So you can put 5, or it doesn't matter if it's degrees Celsius or Kelvin. It just matters when you look at this. This is usually in Kelvins, but it doesn't really matter. You can use both. You don't need to add the 273 to each just to get your answer. Doesn't matter, your change is going to be the same. So here's a practice question. Again, I think it might be really useful. We've only got after this, we've only got about 10 slides left, which is just going to go very quickly through sort of anaerobic respiration and photosynthesis. Aerobic respiration. We also go through anaerobic, but aerobic respiration mainly. Quickly have a go at this question. So we have a 1.56 gram sample of a hydrocarbon mixture, which includes methane and ethane, is burnt. The heat produced was used to heat up 2 liters of water, initially at 20 degrees. The final temperature of the water is 55 degrees Celsius. Determine the energy content of the fuel in kilojoules per gram. Assume all the energy released was transferred to the water. So have a go at this question here. It's a little bit more advanced than what you're probably used to from year 11, but I want you to have a go at it, and we'll go through the answers. Maybe take 3 or 4 minutes to have a go. So 3, 2, 1. Pause, and all right, hopefully you are back. So first of all, we need to figure out our mass of our water. So we have 2 liters of water. We need to multiply that 2 liters by 0.9. Is it 987 or is it 997? Let me have a look. I think I might have used the wrong value there. I think I might have used the atmosphere's value. It's actually 997. I do apologize. I've used the wrong value there. So the answer that you'll get out of this will be slightly wrong. I do apologize for that. I've used the atmosphere's one for some reason. This is slightly off, but let's just work with this value for now. Let's just assume this is how many grams you had. Your answer will be slightly different, but if it's along the same method, then you're right. So we need to find our energy. So we go Q. We need to have this in grams by 4.18 by 35 degrees. This is 55 to 20, so it's a 35 degrees Celsius or 35 Kelvin change. We end up with this many joules, which is a lot, so let's just simplify it down to kilojoules. It's a little bit easier. The answer wants it in kilojoules, so let's just divide it by the 1,000 to make it kilojoules.